Okay, in this section, we're going to look at how to actually balance redox reactions. Now, some redox reactions are easy to balance. What you're going to actually find out, the process that we do here is a little bit more complicated. I shouldn't say more complicated. It's a little bit more involved than what we would have to do. But the majority of redox reactions are actually kind of hard to balance the traditional way that we've learned since Chapter 8. So if you can imagine going back all the reactions we've been balancing, the ones that were the most difficult for you, more likely were a redox. So we're going to find an easier way to balance those more difficult ones. Simple thing is we're going to talk about divide and conquer. So as we go through this process, obviously we've got to have a formula equation and a net ionic equation. We need both of them. Otherwise we can't do this. There seems to be a lot of statements here, but if we go through these one by one, this is the most systematic thing that we probably will do in terms of a chemistry calculation or any type of thing we do. So number one, we got to assign oxidation numbers to every atom. Right? So we take those net ionic equations, formula equations, and we do that. Number two, we've got to then identify what's the oxidation half reaction and then what's the reduction half reaction, and we write them as net ionic. Okay, so we'll be building off of the net ionic, and then we got to balance atoms. Okay? So as we kind of go through this, let me do a simple one here to go through. The one we would have done earlier in the year, we took copper and we added silver nitrate to it, and we ended up making silver metal and copper nitrate. Remember, that was the silver lab that we did. So this is aqueous. That was a solid. Okay. And we had aqueous copper nitrate. Now, net ionic. Okay, copper plus Ag plus NO3. Ag plus Cu plus 2 NO3s. Okay, so there's our net ionic. Now what we have to do is assign oxidation numbers to each element. Copper by itself, pure form, 0. Silver, already a +1. We come in here, oxygens are -2s. So there's 3 -2s, that's a 9 -6. Nitrogen's a 5. Silver is a compound, or an element, is 0. Copper's a 2+. And again, we got nitrate again, so oxygens are -2. Nitrogen's a +5. Okay. So we've assigned oxidation numbers to everything. Now if you notice, copper started out the reaction as a 0. It changed to +2. Silver started out as a +1. It changed to 0. Their oxidation number changed. There's our redox reaction components. We notice nitrates, in the nitrogen, oxygen, and nitrates did not change. Now you're going to notice this is an easy one to balance the old-fashioned way, but we want to go through that redox process. So what do we got to do? We got to identify what was oxidized and what was reduced in the half reactions. So it doesn't matter which one you write first, but I got copper here, so I'll do this. Copper went from a 0 to a 2+. That's what was oxidized. Its oxidation number increased, 0 to 2. Silver was involved in the reduction. It went from a +1 down to a 0. So in simplest terms, there's our redox reaction, okay, our half reactions. Now, next thing we're going to do is we've got to balance elements that are in the half reaction. We balance non-oxygens and hydrogens first. Well, that's easy because there's one of each on each side, so nothing to do there. The next part, it sounds complicated looking at all those words, but it's actually pretty simple. If there's oxygens and hydrogens in there, we have to balance them. And here's how we balance them. Everything's aqueous. There's a lot of stuff that's aqueous. So if we have to balance oxygens, we're going to use water to do that. So if I get too many O's on one side, I'll put waters on the other side to balance it out. And in the end, it's all going to work out. If I have to balance hydrogens, I'm going to use H+. Okay. Now, I have this written twice, and I say if it's acids involved or a base. Here's the thing. A lot of redox reactions are acidic or basic, but this step doesn't change for either one. So you do exactly that. Look at the reaction. Nothing else to balance there. So then we get to the last thing that we've got to check. So we've got to balance the number of electrons in each half reaction to get a complete half reaction. Then the number of electrons in each reaction must be equal. If not, multiply. So if I look here, I went from a copper 0 to a copper 2 plus. And I went through oxidation. So oxidation is lose electrons is oxidation. So what that means is that copper that was a 0 charge, 0 oxidation number, went to a 2 plus, 2 electrons were separated from it. Silver ions had 1 electron added to it. Now, if I were to say write the complete half reaction, this is where we'd stop. That would be our final answer. But if we're trying to balance it, the number of electrons in each half reaction must be equal. If not, then multiply and add the reactions back together. Okay. So again, we divide, now we're going to kind of conquer. So now if I realize here, all right, I don't have the same number of electrons. Now if I add these two reactions together, I've got 2 electrons plus 2 silver ions plus a copper atom makes a copper ion plus 2 silver atoms plus 2 electrons. Now we can see what exactly happened. 2 electrons were involved. In the beginning, 2 electrons, 2 silver ions, and a copper atom were involved. And in the end, we had 2 electrons, or a copper ion, 2 silver atoms, and 2 electrons. Now if we cancel out the electrons on both sides, here's what exactly happened. Okay, so we look at this, we're going to have 2 silver ions plus a copper atom makes a copper ion plus 2 silver atoms. So this is exactly what did change. So those 2 electrons that were with copper went to the silver ion. When that happened, we had a copper ion produced and then ended up with 2 silver atoms. Now, we're going to take those reactions, add them back together, do that. Now, if it's a base reaction, it's not a base, so we don't worry about that. Transfer coefficients from the net ionic reaction to the overall ionic and balance any spectator ions. So what we're going to do is we're going to take that original reaction right here. Bring it back down here. I take the coefficients from the net ionic and carry them down. And then we're going to look at the reaction and see if there's anything else that's not balanced, because those would be spectator ions. And actually, in this situation here, everything is balanced. There is nothing left over that can't be done, or that needs to be balanced. Okay? Now again, it seems like a lot of extra work to do where you could have just put a 2 in front of the 2 silvers and been done with it. You are right, it is. But what you're going to see is reactions are a little bit more complicated than that. Okay? And we will do a couple of those a little bit later.